Hello, Matt Davis here with section 2.2, definition of limits. We looked at the idea of limits in the previous section, but we didn't really define it. We just kind of played around with it. So now we're going to give an informal definition. We'll get to a rigorous definition later in the chapter, but this one that we give now is the one that we tend to think about most of the time when we do limits. So it says, if f of x gets arbitrarily close to a number L as x gets closer and closer, sufficiently close, to a from both sides, then L is the limit of f of x as x approaches a. And then we have a shorthand for that. We write the limit as x approaches a of f of x equals L. So now what does that idea look like in the picture? So the idea is we're moving along a function, getting close to some point down here, a, which we've got this dashed line representing, and I'll draw that line up a little bit higher. And we think about as we're coming along the function and we're getting closer and closer to that dotted line, so as our x value is getting closer and closer to that dotted line, what happens to the y value? And so in this particular one, as we move along the function and we get closer and closer to the dotted line, it looks like we're approaching this point right here. And the height of that point is the value of the limit, which is 4. So the limit as x approaches 3, or the limit as x approaches 3 of f of x using the shorthand of this first function is the number 4, because that's the height that it looks like our function is approaching as the x value approaches the number 3. So if we look at that same idea here, x approaching 3 from either side, as we get closer and closer, it still looks like we're coming towards that same point, which has that same height of 4. Notice in this case that we have the actual value of the function is up higher, but the actual value of the function does not actually matter, and we see that down here. It says the limit describes the behavior near a particular point, not necessarily at the point. So we're not worried about what is the actual height of the function. I like to think of it as this idea of this is a wall and you're coming along the function, so you're going to probably hit that wall as you keep going from either side. And the limit is the height it looks like you're going to hit the wall at. It doesn't matter how high the function is, like inside the wall. If you were cruising along this curve and you were going to hit the wall because of the path you were on, what height does it look like you were aimed at? And in this case, just like the other cases, it looks like that height is 4. So the limit in every case, these 3 cases, is 4 every time. That's true. Let's see if we can erase this so we can see underneath a little bit. That's true when the value of the function is 4. It's also true when the value of the function is different from what it looks like we're going to collide with, and it's also true if the function is undefined at that point altogether. So the limit is really just saying what does it look like the height is going to be, and it's not really concerned with what actually is the height. And that seems a little bit strange, but there's some reasons for that, and we start to see that a little bit with this example. So let's look at the limit as x approaches 4 of the square root of x minus 2 over x minus 4. So let's go ahead and put some function notation on that too. So let's let f of x be equal to the inside piece. So let's say f of x is the square root of x minus 2 divided by x minus 4. And then let's look at this idea of like which of these situations are we in up here. Is the function defined at that point? Is it defined differently at that point? Is it undefined at that point? So the value we're approaching is x equals 4. So let's plug 4 in and see what we get. So if we plug 4 into the function, on top we get the square root of 4 minus 2. On the bottom, we get 4 minus 4. So the top, the square root of 4 is 2, minus 2 is 0. And the bottom, 4 minus 4 is 0. And if we have a 0 in the denominator, then our function is undefined. So the value of the function is undefined, which makes it look like we're in this kind of case C up here, where there's possibly a hole in the function. But just because the function is undefined there doesn't mean that there's not some height the function is approaching as we get close. So we're going to play around with that idea by making a table and seeing what value it looks like we're getting close to. So I'm going to go ahead and make that table here. And we're going to plug a lot of different values in for x. We're going to start out approaching x from the left-hand side, so we'll plug in numbers a little bit less than 4. Sorry, approaching 4 from the left-hand side. So a little smaller than x, numbers like 3.9, 3.99, 3.999, and then we'll just kind of go overboard here at the end, and we'll go 3.999999. And we'll see what happens in all of those cases. So you might wonder, if we want to know the limit at 4, why not just plug in 4? But we already tried that, and when you plug in 4 into this function, it ends up undefined. So we want to find out what it looks like the function's getting close to, even though it's undefined at that point. So how do we do that? We plug into the function. So let's go ahead and switch over to the calculator and play around with that idea. So similar to what I did in the last section, I'm going to take the number I want to plug in, 3.9, type it in and press enter, and then that will be stored in the answer variable, which is above the negative key. So now I want to type in my function using the answer variable in place of x. So the numerator is the square root of x, so second square root, and instead of x, I'm going to type answer. So I want the square root of the answer, end parentheses to end the square root, and then minus 2, and then end parentheses to end the numerator, divided by x minus 4, but again, I'm going to hit second and answer and use that in place of the x and have x minus 4 down there. So there's my function where I've plugged answer in place of the variable, and before I did that, I stored 3.9 into answer, so when I pressed enter, it plugs 3.9 in for each of those spots that says answer, which means it's like it's plugging the 3.9 in for x in the original function. So we get, if we round to 4 decimal places here, 0.2516. So let's go write that down in our table. So the f of x value was approximately 0.2516. So now let's try getting closer to the x and see if there's a trend on what the y value is getting closer to. So we're going to go back. I'm going to type 3.99 and press enter. So now that's stored in answer. And if I hit second and enter, it pulls up my last computation. Hit second and enter again, and I get the previous one. So if I press enter, I'll be getting the value of the function evaluated at answer again, but now answer is 3.99, and the value when I do that to 4 decimals is 0.2502. So let's write that one down. So 0.2502. So it kind of looks like perhaps the y value is getting closer to 0.25 as x gets close to 4. But let's do these next two and try and confirm that. So going back to the calculator, I'm going to put in 3.999, getting a little closer, my x value a little closer to 4. Press enter to store that in answer. Press second enter twice to pull the function back up with answer as the variable. Plug that in. Yeah, that looks like it's getting closer to 0.25. In fact, rounded to 4 decimals, that would be 0.2500. And then let's try the getting carried away version. So put 6 nines in there. Pull up the function by pressing second enter a couple times. Plug that in. And yeah, it looks like it's getting closer and closer to 0.250. So if I go back over here, we can write these rounded to 4 decimal places. And to 4 decimal places, they both end up being the same, which is a pretty strong indication that that's probably what the limit is going to be. But let's do a little extra work on this. Let's plug in some values from the other side and see if we see the same pattern from that other side. So I'm going to plug in numbers where the x value is getting close to 4, but we're going to make it bigger than 4 and getting close to 4. And then we'll do 1, 2, 3, 4, 5 zeros and a 1 to kind of mimic what we did on the other one. Those are the x's. We want to plug them in. See if we get the same pattern of approaching 0.25. So we go back to the calculator. 4.1. Pull up the function. That's what you get when you put in 4.1. 4.01. Second enter a couple times. Plug that in. So it looks like the 4 decimals we're getting 0.2485 and 0.2498. Let's go write those down. So 0.2485 and 0.2498. So it looks like we're getting close to 0.25 again. And it's always kind of nice when on this one over here, we're getting values that were smaller and smaller and approaching 0.25. And now it looks like maybe we're getting bigger and bigger values approaching 0.25. That's a really good indicator that 0.25 is probably the right answer for the limit. Let's go plug in these next two values. So 4.001, store that into answer, plug that into the function, getting very close to 0.25. In fact, if we rounded that to 4 decimals, it would be 0.2500. And now 4.12345 and a 1, store that in, second enter twice, plug that in. We got all those 9s showing up there. Definitely would round to 0.2500 again. So it looks pretty solidly like that is probably the limit. We're going to find techniques later to kind of know for sure if we found the answer. But right now, when we're doing this table method and we're getting this kind of same answer, whether we come from the smaller number side or the bigger number side, and it seems to be settling down on an answer, that's a pretty good idea that we found the actual answer there. So it looks like the limit as x approaches 4 of the square root of x minus 2 divided by x minus 4 really looks like, but I'll put a question mark because we haven't really proven it. We've just kind of got a good guess here. Really looks like that's 0.25. So that's what we're going to go ahead and put for our final answer on that one. We can't get rid of that question mark until we find some rules that we know are finding the limit. When we use the table method, we're just guessing. But so far it looks like we've got a pretty good guess at it. All right, so in the work that we just did on the previous page, we looked at approaching 4 from the left, 3.9, 3.99, 3.999. And then we looked at approaching x from the right, 4.1, 4.01, 4.0001, approaching 4 from the right, I should say. That idea of approaching from one side versus the other is called a one-sided limit. So the left-sided limit is if f of x is arbitrarily close to L for all x sufficiently close to A and on the left of A, or x is less than A. And if we have that, we write the limit as x approaches A from the left, and we put a little negative like in the exponent spot on A to read that we're approaching A from the left of f of x equals L. And if the same thing is true where x is greater than A, then that is referred to as a right-sided limit. And the way we would write that one is the limit as x approaches A from the right, and we say from the right by putting a plus in like the exponent spot on that A. So that's the shorthand for the limit as x approaches A from the left when we use the negative sign like an exponent, or the limit as x approaches A from the right of f of x if we put the plus sign in the exponent spot. Now if we look at this picture right here and we look at x approaching 2, so let's kind of put that wall idea, you can see that if we're traveling along the function from the left towards that wall, the height that it appears we're going to hit is different than if we were traveling along that function from the right and going to hit the wall. So we can use that idea of hitting the wall, the height at which we hit the wall being the limit, to use this graph to answer these questions about what is the limit as x approaches 2 from the left or the right. So the limit as x approaches 2 from the left-hand side of f of x is that height that it appears that we are on a collision course with when we come from the left-hand side. And if you kind of are traveling along that function, it looks like you're going to hit the wall at a height of 3. So we would say the limit as x approaches 2 from the left is 3. If you're looking at the limit as x approaches 2 from the right-hand side of this function, then you're traveling along from this direction, and you look at what height does it look like we're going to smash into the wall at, and that's this height right here, which appears to be 5. So if you imagine us traveling on this function from the two different sides and hitting a wall that's drawn at x equals 2. The height from the left is 3, the height from the right is 5, and that corresponds to the left and right hand limits. So then what does that tell us about the overall limit? Well, in order for the overall limit to exist, you have to have the two sides agreeing. So whenever you get a different answer from the left and the right, we end up saying that the limit as x approaches, in this case 2, of the function does not exist. And I often use this shorthand DNE in that case. So again, that stands for does not exist. So we'll talk about that a little bit more formally on the next page, but that's the idea. Those two need to agree in order for the limit to match. So let's look at one where the graph isn't drawn, but we start off with a piecewise defined function. So we're going to define here the function one way if x is less than 0 and a different way if x is greater than or equal to 0. And that will often make an interesting limit at 0 approaching from either the left or the right hand side. So either from the left or from the right. Okay, so let's go ahead and work on the graph piece of this. So if you're working on the left-hand side, that's going to be this piece right here. And so you think about, what does y equals negative x squared plus 1 look like? Well, that would be a parabola that opens down and is shifted up 1 unit. So let's start off by drawing some axes in on our curve here. We've got an x and a y axis. Let's say that every other one is an integer. And we'll go ahead and do the same thing over here. So half, 1, 1.5, 2, 2.5, 3. Same thing in the negative direction. All right, so if we were to draw this parabola, up 1 unit for the vertex, and then opening down, then it would look something like this on the left-hand side, and we'd have the mirror image on the right-hand side. I'm going to draw that as a dotted line, though, instead of a solid line, because we only have this parabola, negative x squared plus 1, when x is less than 0. In fact, I drew an open circle there, but because it's strictly less than 0, we shouldn't have that right there. It should be open. So we'll do open circle and then draw that in. All right, so then what about on the right-hand side? On the right-hand side, when x is greater than or equal to 0, it looks like 2x plus 1, which means it looks like y equals 2x plus 1. So what is that? That's a line with slope 2 and a height of 1. So that circle now gets filled in by that height of 1, and over 1 up to, the line would look something like this. And it would continue this way, except for that we're only defining it to be the line when x is greater than or equal to 0. So our graph is just this part that I'm going to highlight for you in yellow. On the left side, it's this parabola. On the right-hand side, it's that line. All right, so what does that mean for limits? Well, what would happen if I took the limit as x approached 0 from the left of this function? Well, if we approach from the left, then we're coming along the function from this way. And what height does it look like we're approaching as we get close to this wall at 0? And it looks like we would hit that at a height of 1. So we'll go ahead and say equals 1 there. Sorry, I was having a little bit of trouble with the pen. So equals 1. So what about if we come from the right-hand side? So what if we were coming from the right? We'd be on the line, but it still looks like we're hitting that same height point, which is a height of 1. So even if we're coming from the right, we still get the same thing. So the limit as x approaches 0 from the right-hand side of f of x is still 1. And by the way, what does that imply or tell us about the overall limit if the limit from the left and the right are the same? then the overall limit is that same value. So the limit as x approaches 0 overall of f of x is also 1, because the height from the collision height from both the left and the right hand side exists and is the same value of 1. So they just asked us to do the limit from the left and the right, but that is something we want to note. If the limit from the left and the right agree, then the overall limit is that same value. All right, we're going to go ahead and wrap this up with one more page with a couple more examples. And in the first one, we're going to introduce a new function called the floor function. So for any real number x, the floor function f of x equals to this kind of bracket with an x inside is the greatest integer that is less than or equal to x. So for example, f of 1.7 is the floor of 1.7, which is equal to 1 because 1 is the greatest integer that is less than 1.7. And if you put in a 1.5, it would still be 1. 1.3 would still be 1. So they want us to graph this for part A. So in fact, if you put in any number that is 1 or bigger, you're going to get a 1 until you get to 2. Once you get to 2, if you take the floor function of 2, the greatest integer that is less than or equal to 2 is 2. So when you get to 2, it jumps up here. And then it goes along, and the floor function of 2.3 is 2, 2.7 is 2. So it stays flat till it gets to 3. When it gets to 3, it would jump up again and start doing this. So it's kind of what we refer to as a step function. Kind of goes along, and then when it reaches the next integer, it jumps up. So the floor of 0.7 is 0, the floor of 0.314 is 0. And then over here on the left-hand side, we'd have something similar going on with that step pattern continuing. So the floor of, let's write this down here and then we'll erase it, but the floor of negative 0.376 is equal to negative 1 because the greatest integer that is less than or equal to negative 0.376 is negative 1. All right, let's go ahead and get rid of that. And let's go back and start working on the next part. Evaluate the limit as x approaches 2 from the left, and also the limit as x approaches 0 for this function overall. So we're looking at a one-sided limit from the left and an overall limit at 0. So let's start off with the limit from the left. So the limit as x approaches 2 from the left of the floor function of x, what would that be equal to? So let's go over to the graph and see what's going on there. So we're talking about the number 2, which is right here. And then we're approaching from the left, so we're coming from this side on the function. So what height does it look like we're on a collision course for? Whatever this open circle is right here seems to be the collision mark, and the height of that is 1. So the value of the function there, or the value of the limit there, is 1. And then how about the limit as x approaches 0 of the floor function? Now here, since it doesn't say which side we're approaching from, it doesn't have a plus or a minus on it, that means overall. And as I mentioned before, for the overall limit to exist, it has to be the same from the left and the right. So let's look at that idea. If we're coming from the left, now we're approaching 0 for our x value. So if we come from the left, it looks like the height we're approaching is negative 1, but if we come from the right, it looks like the height is 0. Since the heights from the left and the right do not agree, the overall limit does not exist. So just to summarize that last idea, the relationship between one-sided and two-sided limits. The two-sided limit, x approaches a with no plus or minus written on it, of f of x exists if and only if the two-sided limits both exist and are equal. And in that case, it would be the limit as x approaches a would be equal to the limit as x approaches a from the left, and, that would be of f of x, and the limit as x approaches a from the right of f of x, and that's f of x in all three parts, so I'll squeeze an f of x in right there. So in order for the overall limit to exist, left and right have to exist and be the same. And in that last case, they wanted the overall limit, and the left and right did exist, but they weren't the same, so the overall limit did not exist. All right, let's look at one more, and this one is going to be for a trig function. So we're going to use a table to find the limit of f of x, where f of x is equal to sine x over x. Looks like we're missing an x there. I'm going to go ahead and write that in. Hopefully I'll have that fixed in your notes by the time you do it, but there should be an x right there. So we're looking at the limit of f of x equals sine x over x as x approaches 0 from the left and right hand side. So we're going to try and do this with a table approach. When you work on trig functions in calculus, unless the problem specifically tells you differently, you always want to make sure that your calculator is in radian mode. That's the standard mode for which we do calculus work. So switching over to the calculator for a second here, if we hit the mode key, it may look a little different for you, but you want to go find, like, where is the trig part. So let's see. Down here is radian mode, over there is degree mode. So I want to make sure that my angles are in radians. So, and mine weren't, so I just went ahead and switched that, and that should make sure that this turns out correctly. So make sure you're also in radian mode. All right, so now let's go ahead and switch back to the notes, and we're going to make a table. So let's set that up. So we're going to take x values, and we're going to approach 0 at first from the left. So that would be negative numbers like negative 0.1, negative 0.01, negative 0.001, and then we'll go a little bit closer, or a lot closer, all of a sudden do negative 0.000001. And then we'll also look at 0 just to see what's going on there. And then we're going to approach from the other side too. So we'll do values just like we had up there, but positive ones, so that we're looking at approaching from the other side or from the right. And then we'll see what all these different values give us. So let's start off looking at the 0 just to see what goes on there. Like, what's actually happening at the function when you try and plug a 0 into it. So if you take the sine function and you plug in 0, and then you divide that by 0, well, we're dividing by 0, so that's going to be undefined. Calculation error divided by 0. So I guess that one's fairly obvious before we even press enter, since we're sticking 0 directly into the denominator. So at 0, the function is undefined. But that doesn't mean that the limit doesn't exist. So let's go ahead and play around with plugging these different numbers in. So, like we did before, we're going to use that little calculator trick. I'm going to put negative 0.1 and then press enter, so that's stored an answer. And then I'm going to type sine of answer divided by second answer. And so when I press enter there, I am plugging in negative 0.1 into that function. And let's go ahead and do the next one at the same time. So negative 0.01 is now stored as answer. Plug that in, and we get these values. So we'll go ahead and round these to 5 decimals, so 99833 and 99998. Let's go write those down. So for f of x, when we plugged in the negative 0.1, we got 0.99833 or 883. Let's see, didn't hold that in the brain good enough. 99833, okay. And then when we plug that in with an extra 0 in there, we got 4 9s and then an 8. So now let's see what happens if we increase the number of zeros, which means we're getting closer to 0. So negative 0.001, store that, plug that in to the function. Now we get so many 9s that if I round that to 5 decimal places, let's see, we have 99999 followed by 9. So that would actually round to 1. And then let's do the one where we put in more zeros. I think I had 5 zeros and then a 1. So that's showing in scientific notation, but it's still stored correctly. And there we actually, it just pops out 1. It doesn't mean that it really was 1, but there were so many 9s that when it rounded it to the number of digits it displays, we got a 1. So for both of those last two, when rounded to 5 decimal places, we got a 1. So that's a pretty good indication that that's probably the limit. But remember, the limit has to exist and be the same from the left and the right-hand side. So let's go check the right and see if we're getting the same sort of stuff. So 0.1 stored and then 0.1 plugged in. Notice that's the same answer we got before. So there's probably some symmetry going on here with the sine function. Plug in with a 0.01. There's that 9998 we got before. Add another 0 and plug it in. That's the one that's first going to round to 1 when we go to 5 decimals. And then when we get a little bit more carried away with the zeros and plug that in, we once again have it just showing us a 1. So let's write those down. So this is kind of the direction we went, right? It was from the bottom up here. So for 0.1, we got 99833. And then when we plugged in something a little closer from the right, we got 99998. And then for the next two, they rounded to 1 when we put 5 decimals. So we went this way and this way. So coming from the left and the right, we got the same thing. So based on our chart, it looks like the limit as x approaches 0 from the left of f of x, which was this case, from the left of 0 means negative numbers. We got a 1. I'll put the question mark because it's from a table, so it's a guess, but it looks pretty solid. And when we come from the right, which was this side, positive values, we also got a 1. So if the left and the right both seem to exist and both seem to be the same, then what's our conjecture about the overall limit down here? We would guess that that is also going to be a 1. Again, because the limit from the left and the right exist and are the same. When that's the case, the overall limit is the same value. All right, so there's a little bit more of a in-depth look at limits, but we're going to keep working on it for the whole chapter. So not necessarily the case that you should have a super firm grip on this yet, but we're just trying to work on the idea and wrestle with it and add tools. So hopefully by the time we get to this end of this chapter, you've seen enough tools that you're getting more and more comfortable with limits. For now, just dig into the homework and the quizzes and start wrestling with the idea.